this computer. There we go.
Cool.
There we go. Great. And like I said, I will turn this into a PDF as well. So you'll have something in your hand a little bit to follow.
Cool.
So
thank you.
You're welcome. On project 2, you will have to have a cantilevered truss. So that's part of what this is. The other is just general, is just also load flow. So that would be something that shows up obviously on project 1 and sort of continuously. And note here, unlike your project, if you notice here, the framing is all given to you. So you don't have to create the framing, but you'd notice here that you've got 1, 2, 3, 4, 5, 6, 7, 8. So that gives us 9 spaces. So these are spaced at 10 feet. So this is all, again, this is all given to you, so you didn't have to make that determination. But that'll be something we use right here when we design truss A. So you've got some numbers here. We're going to do something with the beams and girders. So this would be a typical beam. We've also got a typical floor depths for the 30-foot beams and girders, and the 60-foot beams, which would be out here, the cantilevers, and then here would be the girders that would be spanning. So we're not going to actually design those, but we're going to just do the depth of them. So let me give you this picture here. So this is what the building looks like in profile. So you've got a roof. All right, you've got a floor. And then you've got the ground down below. So this would be this truss that you would be looking at. That would be truss B. So I'll go back up to the top again. So that would be looking, if you will, that would be looking in this direction. That's an eyeball right there. Looking in that direction. And so truss A would be into the plane of the page. That would be where truss A is. So truss A is being supported out there on the far edge of truss B. Okay, so got a couple things written, and then we'll end up I'll create some more here. So from the LRFD, the load, you're gonna do 1.2, right, times the dead load, 1.6 times the live load. And so you've got your roof load in pounds per square foot, and then also your floor load in pounds per square foot. So I'm gonna take a look at truss A here for just a minute. The way that the load flows, we'll end up designing truss A because truss A is held up by truss B. So truss A, right, is 90 feet in length. It's going to be 15 feet tall. And the point of what I want to talk about here is that you've got a roof load. One second. Some more people. So we've got a roof load. And so that roof load is going to come from the 128 pounds per square foot. And then we need to multiply by the tributary width. So I'm going to go back to the floor plan. And I'm going to give a little dash right here. And so there would be there's the tributary area. And so that 30 feet right there would be I'll do it up here. That 30 feet would be the tributary width that delivers load to the truss. And there's more than 3-point loads, so we're going to smear them to a uniform distributed load. And so you're going to take that 128, multiply by 30, and so you end up with about 3.84 kips per lineal foot. Now that would be from the roof. On the floor, right, we've got a different load. We've got 224 pounds per square foot, and we still have a tributary width of 30 feet, and that then ends up with about 6.72 kips per lineal foot. Now I'm going to use this concept here. And so this truss, technically it has loads on the top chord and on the bottom chord, but that would get a little bit more specific about into the design of the truss. All we're going to design are the top and bottom chords. And so that load is statically equivalent. One moment. So it's Eric. Yes, I'm actually also recording it as well. So I'll put it on the, close that. Second, admit. It's a little bit of juggling here. All right. So that truss, that 90-foot truss, we're going to be able to design it like using what would be a statically equivalent load of just putting both loads together and thinking of it as being on top would be one way. So what I would say is we're using actually a beam analogy. So we've got like a 90-foot beam, and we've got a uniform distributed load. And so that load is going to be 10.5 kips per lineal foot. And the fact that the beam is actually a truss is then a little bit secondary. That's what we end up dealing with afterwards. But in terms of, when we're going to find the moment, right, we can use, if we needed to find the maximum shear, right, we would use this single beam analogy to do that. So the fact that this shaded region down there is a truss is what allows us to have a 90-foot span. When if we had a solid beam, not only would you have a huge cross section, it would just weigh too much to be able to span that far. All right, so let's go ahead and just kind of work our way through. All right, so I'm going to go back to just real quick to get a view here. So we are asked to determine the depth. So just the depth, not have to size it, right? For the 30-foot beams and girders and for the 60-foot beams. So this actually is going to go very quick. Again, this is just minimum depth. So this is the span to depth requirement. So for the 30-foot floor beam, so we're going to use L over 15. I'm sorry, that's for the girder, excuse me. So the minimum, is L over 20. And so we put our 30-foot, we've got to go 12 inches per foot, divide that by 20, right? Keeping our units, so we need an 18-inch depth. So for those 30-foot floor beams, we would end up using a W18 by ... We would do something based on the moment that the beam would be expecting. All right, for a typical girder, and on that floor plan, the girders were 30 foot. And for a girder, it's L over 15. And so it's shorter. Those girders are going to have more load on them. And so we've got a 30 foot times 12 inches for 1 foot divided by 15. So that's going to give us about 24 inch. So you would use a W24 by ... Again, if you could, or you would use a larger, a deeper section. That would just be the minimum that would be needed. So let's go now for the typical 60-foot beam. Oops. I wonder if that's what does it. The typical 60-foot beam. And so we would still use for a typical beam L over 20. And so we'd end up with 60 feet, 12 inches over a foot divided by 20. And so we'd get about 36 inches. So we'd use a W36 by for a typical 60-foot beam. We will do truss A. So let me go back to the framing plan up here. All right, so we're going to design this, right? That truss right there. We would end up with a free body diagram. So I'm going to go ahead and draw a truss. I'm probably not going to come up with the exact right number of these, but from a dimension point of view, we know the truss is full story height, so that would be 15 feet, and each bay is going to be 10 feet, and that comes from the framing plan that was given to us. So again, I might come up not exactly correct there, but we've got dimension-wise total of 90 feet. Right. Over here, we've got a reaction. At both ends, we've got a reaction. So I'm just going to call that R1 and R2. And so on the truss, right, and we're going to, because there's, right, more than 4 point loads, we can smear it. And so this is what we had calculated earlier. That would be the 10.5 kips per lineal foot. So let me just kind of go back. That's what we just did right here. So we're right to this point, right? We've done some preliminary depth sizes, at least, for those beams and girders, right? We're right here on truss A. We're going to end up using these reactions because they end up being loads on the other truss, on the other truss. So we've got to do just a little bit of statics here. So you can go some of the moments at the left end. That equals 0. Oops. All right, you could do that. You could use the concept then of, again, it's a very powerful concept. You could use the statically equivalent point load, and you would get that by taking 10.5 kips per lineal foot. You're going to multiply that by 90 feet, and it's going to end up going right in the middle at 45 feet. So you could also just use the fact that it's a symmetric loading. And so either one of those would give us, in the end, we would find that R1, actually if we do it at the left end, it would be R2, is going to be equal to 475 kips. And also that some of the forces in the y direction, or by symmetry, we would also know that R1 is equal to 475 kips as well. So we've basically used a very strong beam analogy here, right? We've solved for the reactions, R1 and R2, by using some statics. And then we can go some of the forces in the y direction. Okay, very basic level of it. And so we're actually ready now to transfer those loads, or what's going to transfer to the cantilevered truss. But first we're going to design the top and bottom chords of this truss. So we can find the moment demand, which is going to be, we've got a simply supported beam with a distributed load on it. So it's going to be W L squared over 8. So we've got W, which is 10.5 kips per lineal foot. We've got 90 feet. That's going to be squared over 8. So that's going to give us a value of about 10,630 kip feet. Also keeping in mind depth requirements for the truss, right? L over 10 is for a truss. So this would require at least 9 feet from a depth perspective. So we've got a truss that's going to be 15 feet that we use. So we're within tolerance there. So this is why we have to use a truss and not go find some W section, is that we'd have a W section that is so huge, right? Or we wouldn't be able to find one that would be able to have that much demand to it. And so what we're going to do then, that's why we've decided to use a truss across those 90 feet for that long span. And so the chord force, goodness, I don't know why it does that. Would be 10,600 kip feet divided by the depth of the truss, which would be 15 feet. So we've got 710 kips. So that would be the chord force, tension, and compression. So that's what's going to be taken by the top and the bottom chord. And so we're going to then have to design, all right, we're going to go in compression. And this is where from the framing here that we've got the length is 10 feet. So sorry. So if we go back here, what we are designing is, we're designing the very middle, that very middle member. That would be where the compression is the largest, right? That's where the moment is the largest. And so between the nodes, we've got L equals 10 feet. And the reason why is because that's what was given to us. All right, that's what was given to us all the way back here. We were given a floor plan that had 8 beams or 9 spaces. So 90 divided by 9 would be 10 feet. All right, so we're almost home here. Then we'll actually just take a break. So this would now be, you would go to page 30 in your handout. And so actually, you know what? I'm going to try and do that with you here. I've got it right here. Oh, goodness. So just to bring you here, we're going to design it using the column table because we've got a member that's in compression. And so we've got a length of 10, so we would have to use there they are. So we would use the 12-foot section, right? We've got 10, so we're going to end up having to round up from, we can't use 9, we'll end up using 10, the 12-foot, and so 710. So we would be right here. So that would be the size of our top chord. So that's how we got that. All right? That's the compressive force, and there's the unsupported length. All right, let's do this. I'm gonna go, we've got the cantilevered truss. Now we're gonna design this one right here. We'll design that, and let's do this. I'm gonna take just a quick, about a 4-minute break. So I'll be back at 4:50. So I will be back, and we will do the last piece of this example. All right, we will finish this thing up. So what we've got here, what we've done, so again, it's similar, right? At least starting wise here, we had sized just using depth, just the depth, that those would be the 30-foot beams would be W18s, right? The 30-foot right there girders, right, would be W24s. And then over here, we've got several beams, right, that would be W36. And so simply supported, right, would be going from truss A all the way back to this column line. And now the way we're going to frame this thing on the outside is to have that cantilever held up, we're going to have truss B. And so that's really the major structural component, right? All the loads from truss A, right, are held up on the end of truss B. So let's go ahead and work our way out there. So now we're at truss B. And so I'm going to draw this thing in profile. So we do know it's full height, right? It's story height, so it's going to be 15 feet, right? It's a total of 120 feet, so it's comes in those two 60-foot sections. And we're going to have reaction, call it R10, R20. And now we need to find the loads that come to it. And so out here, actually, let me do this. Let me just to specify that this is a truss. Now we haven't designed exactly what the node spacing is. We'll talk through that here in just a second. But all the way out here, this would be truss A, and that delivers 475 kips. That's the reaction that we had at the end, right, at both ends of truss A. Okay, we're going to have a distributed load. So we're going to use that same concept that it would come both from the roof and from the floor plan. And so really what we're going to need is the tributary width is going to be most important here. So this is going to be the 128 plus 224. Those are in pounds per square foot. And then we need to multiply by the tributary width. So let's go back up to the framing plan. And so if you notice here, we've got tributary. It's actually very small. The width is only 5 feet. The other 5 feet go to the beam, right? That's framed in, that then delivers load from, right? That delivers load then from the girder. So this one goes straight into the column, but we are going to need to pick up the reaction from that girder right there. So we're going to have another point load that carries, right, by statics, the reaction from the two beams that it's holding on both sides. So I'm going to get down here. So this is multiplied by 5 feet. And then we've got one more reaction, and that comes from that other girder. And it turns out that that's going to be 106 kips. So I'll include that calculation. I'll show you a little bit more about that in the when I give you the sort of the PDF of it. So there's our truss, and we've already got a height. And so we're just going to design, when we say design a truss, what we're designing top and bottom chord. And so unlike truss A, which had some nice symmetry, there's clearly no symmetry here. So what we're interested in doing then is we're going to have to do statics. So we would be interested if we were doing load flow, if we were finding some column loads, right? We'd have to find our reactions. So you could sum moments, again at the left. Some moments at the left end. So you could go ahead and do that. That would give you a chance to find R, I don't know why it does that, R20, which is equal to 6. It seems like there's just an amount of time before this happens. 636 kips. And then at this point, you could sum forces. So the same procedure, sum forces in the y direction. And you would find that R1 was equal to 161 kips. So those would be the reactions, again, just from the truss loads. So what we're seeing here is just an appreciation for truss B, right? Truss B is, we are going to design it for its top and bottom chord forces. Right? If you do remember from the handout for a cantilever truss, it's going to be L over 4. And so, and it's L of the cantilever, so 60 feet over 4. If I've got that right, if I don't have quarantine brain too much, then I've got 15 feet, which actually turns out to be the, story height. So that's a reason why that truss needs to be full story height. So what we need to do is find the M demand. And so I would not, it's really frustrating. So one way to do that would be to draw the shear in the moment diagram. I'm sure you're not very interested in doing that. What I can tell you though is this will happen at the support. So for the cantilever, we would know that back here, there's 0 moment because that's like a pin connection. So the moment that we're going to find is going to be right over the moment inside the truss, right over the support, the internal support. And so you can do that a couple different ways. And really the best way would just be to cut a free body diagram. So we'd have out here, there's the 475 kips. We'd have the distributed load that would show up. And what you'd be interested in doing then is solving for M internal. So you would also have a shear. And so we can avoid solving for the shear by just summing moments at the cut. That would be the quickest way to go ahead and solve for that internal moment. And so if you did that, right, and I will give you this on the handout. If you did that, you would find that the internal moment right at that support is going to be 31740 kip feet. All right, so I would encourage you to go ahead and do this. Again, you need your distributed load to do that. Sorry, it's a little sticky. There's your distributed load that you would need to use on there. You need to calculate that value. And then lastly, so we're actually right at the home stretch. So there would be the moment. And so the chord force would be the moment. Boy, I don't know why it does that. Would be the moment divided by the depth. So we'd have 31740 kip feet divided by the depth, which is 15 feet. And so that would give us 2116 kips. And so what we're going to say is that we'll go and look at a couple of different options here. We can look at L of equal to 10 feet. Oops. And so when I mean L, we're talking about the length here, the node distance on the top and bottom. So we could use 10 feet, and then we're going to go to page 30 again and say, or we could use L of equal to 15 feet. So we'll take a look at both of those. All right, we are right in the home stretch here. We're right back to this. And so if we use the 10-foot bay length, then we would, our number was 2116. So we'd be right here. We would use 2116 is just below 2180. So we would use right there, we would use 12 by 90. Now, if we used instead of 10 foot, if we used 15 feet, which would be available to us, right? You can see the trade-off here is that then we would have to use a larger section. We'd use a 14 by 211. And so I'll go back to the sketch here and we'll finish up. So as we design our truss, so we do know that this truss is 15 feet tall, and so we're talking about, right, this distance. So we could use L of 10 feet. All right, and if we did that, we would be using W 12 by Goodness gracious. We'd be using W12 by 190. And if we used instead an L of 15, I have no idea why those lines are disappearing. We would use W14 by, what was it, 230? And so here's some of the trade-off here, right? If you used an L of 10 feet, right, you could use smaller members, but you'd have more diagonals, right? We've got something that would be, it's 120 feet in total length. So you'd either have 12 bays, or if you used L of 15 feet, you would have only 8 bays. So there'd be a little less material, right, on the diagonals because you'd have fewer diagonals if you used an L of 15 feet. And if you used an L of 10 feet, you'd have 12 bays, but you'd have smaller members. So, all right, so I will give you that. I will give you that in a little bit of PDF form. Stop sharing. So that should get you, right, a little bit more with Trust Design. You might have in your project one, right, you might have a cantilevered truss. You might not. It didn't look like we had very many that were cantilevered, but you may have found one. So that might help you with that, or just with your normal truss design. And I'm looking forward to seeing your project ones. So it's 5:05, and so we've got this. I will be here until 6 on this. So if you guys would like to consult at all with your group, or you just had another question, that's completely fine. So I would be available to talk with you guys. That project one, right, is due at 8 p.m. on Thursday. And so that kind of finishes a cycle for us with a homework and a project. Like I said, go ahead and take a look at, there's class 5 is a page on Canvas, and go ahead and look at that as well. That'll make sure you're aware of what's due at the submittal for project 1. Let me just go back one sec here to share that again. So I talk about that on our class page, going over what needs. Just go ahead and look at the assignment sheet again. You don't have to do any calculations for a lateral system, but you do need to obey those concepts of balanced placement, vertical continuity, and just adequate strength. So you need to have enough, if that makes sense. You have enough lateral systems smartly placed. So we start to get into that here with the asynchronous lecture, and then we do that again next week with a synchronous lecture on lateral loads. And so, like I said, next Thursday, class time, you'll expect we'll probably have about 30 to 40 minutes, probably more like 30 minutes of lecture. It piggybacks off of this. And then you will have an in-class activity. So you'll do something in a group. I'll put you in a group again, be the same group you have for the project. And so that'll be due by 6. That's next week. All right. So you guys can do however you want to do it. If you want to leave and come back, yeah, that's completely. I can look at anything you guys would like. So if you guys just want to hang out and ask me like in a public setting, or if you want to kind of leave and then come back as a group, I will be here until 6. So I'm not going anywhere. So you guys can leave and come back if you'd like. Okay. Thank you guys. Thank you very much.